Okay, a rather oddly worded question. Find lambda such that this 3 by 3 matrix is singular. Singular means non-invertible. Well, we know how to take determinants, and we know it was theorem 4.3. By theorem 4.3, a matrix A, say, is singular if and only if its determinant of A equals 0. So here's the plan. Let's find the determinant of this matrix, set it equal to 0, and see what that implies about lambda. Now, this is an odd-looking question on the surface of it, but it's going to play a big role in section 4.3. No, take it back. In chapter 5, when we do eigenvalues, these kinds of computations will be all too common. Okay, so let's consider the determinant of this 3 by 3 matrix. Determinant of the matrix, 1 minus lambda, then zeros below that, 0, 4 minus lambda, 4, final column, 2, 3, negative lambda. Okay. Let's expand along a convenient row or column. Gotta love the first column because it's got 2 zeros in it. Okay, so we'll take the entry, 1 minus lambda, multiply by the determinant of the associated minor matrix. And let's leave a few details out of this one as compared to what we've done in the past. Let's not do anything extra. Okay, here's the minor matrix. So that minor matrix, 4 minus lambda and 3 for the first row, 4 and negative lambda for the second row. Okay, we'll move down, introduce a negative sign, and take 0 times, well, whatever. It's going to be 0. Move further down, 0 times, whatever. Powers of -1, which are actually taken care of with the minus and the plus. And then determinants of minor matrices. So that's the advantage of using the first column. I don't need to figure out those determinants of minor matrices. We just need to do this one. So we've got 1 minus lambda times diagonal minus back diagonal. So that would be 4 minus lambda times negative lambda along the diagonal minus 3 times 4. Okay, so we're producing the determinant. Remember, we're going to want to set that equal to 0. That's how we'll find the lambdas. All right, so let's see, that's 1 minus lambda. I still need to do some factoring here. 1 minus lambda, I guess I have to multiply this out. That will be -4 lambda plus lambda squared minus 12. Maybe 1 minus lambda times lambda squared minus 4 lambda minus 12, more amenable to factoring in that form. So what do we need? Lambda minus 3. Nope, let's try lambda minus 6 and lambda plus 2. I'm going to give this lambda squared minus 6 lambda plus 2 lambda, minus 4 lambda minus 12. That's it. Okay, so the matrix is singular when its determinant, and we've got its determinant in terms of lambda here, its determinant 1 minus lambda. So let me write this in a slightly different order. Let's write it as lambda plus 2 times 1 minus lambda times lambda minus 6. When that determinant equals 0, I've got my reasons for writing it in this order, then by theorem 4.3, the original matrix is singular, non-invertible. All right. this occurs, good opportunity to use a semicolon. This occurs when lambda equals -2, or lambda equals 1, or lambda equals 6. When any of those are the value of lambda, then the determinant of that matrix over here is 0, and that's a non-invertible matrix. Little notational thing. I've listed these lambda values in increasing order. -2 is less than 1 is less than 6. I got my reasons for that. We're going to do a lot of this stuff, and just between you and me, I want to list those lambda values from lesser to greater whenever we do one of these, just for some consistency. It'll be useful when we do chapter 5 in the eigenvalues and eigenvector stuff. But you want singular, that means you want the determinant equal to 0. And I got no other way of going at this. I can't do any row reduction on this because I don't know what lambda is. It would be nightmarish. Try it, you'll see. The way to go is by taking determinants, setting them equal to 0, and factoring the result. Factor, polynomial, there you go.